Okay, in the second part of Chapter 4, we're going to look at Section 4.5, which deals with coding categorical predictor variables. So if you remember earlier, back in Chapter 3, we looked at categorical variables that were binary, like the growth rate example for children. We categorized, one of the variables had to do with gender, so we had indicator variables whether the child was a girl or a boy. But in the past, we only dealt with categorical variables that had two options. We want to think about what do you do with categorical variables that have more than two options? How do we categorize now and include those variables? Okay, so the example that we'll look at in this section in Chapter 4 looks at car prices. And the data set involves, in part, car prices for Hondas, Maximas, and Mazda 6s. And their average price and standard deviation are given in this table, and this average prices are in thousands of dollars. So we can see that there does seem to be a difference in average prices for the cars, and we might want to think about coming up with a model to predict price that will include, in part, the type of car that we have. So one way we could think about doing this is to make an indicator variable for Accord. 1 if the car is an Accord, and 0 if it's not an Accord. And we could do the same thing, right, for the Mazda 6. We could let it be 1 or 0, depending if the car is a Mazda 6 or not a Mazda 6. And similarly for a Maxima. The deal is we do not want to include all 3 indicator variables in our model. And I really suggest that you read the, at the bottom of page 175 talks about this issue. So what we'll want to do is just to fit 2 of the indicator variables. And so we'll decide to drop the Accord variable. It doesn't matter which one you drop, but whenever you have an indicator variable that has K options, just drop one of them, so you're going to model with the remaining K-1 options. Okay, in the data set, the car data set, the indicator functions are already made for you, but I just want to point out that if they're not done for you, this is how you go about doing it. So in Minitab, if you click Calc, you'll see Make Indicator Variables, and then there'll be a pop-up window. So we wanted to do it on car type, right? Accord, Mazda, or Maxima are the values that are in the car type category. So select that here. And then down here, it fills in these names. You could give them new names. Just call this Accord, Maxima, and Mazda 6. But what it will do then is apply 1s or 0s, depending on whether the car is an Accord, a Maxima, or a Mazda 6. Since we didn't include Accord in the model, well, we'll see. Actually, pause on that. We'll get to that in a minute. Okay, so what you can do now is just, let's look at building a model, and this is just doing the usual regression model that we've been doing in Minitab. So once you have your indicator variables in, you'll just go and fit a regression model. The response is price and the continuous variables. We're just going to include for now what type of car it is, whether an Accord, a Mazda 6, or a Maxima. Okay, and so the variables we're modeling with for cars type are Mazda 6 and Maxima. So if you run that model, you should get this regression equation. Okay, and I just want you to stop here and pause and notice a couple of things. I recopied this table that was on a couple of slides ago. Notice it's 14.277. That's exactly the mean price of the Accord. Okay, so when we leave the Accord out, the y-intercept in this model will always be the average price of that variable, in this case the Accord. We see the coefficient in front of the Mazda 6 is negative 2.77. And remember how we want to interpret that. So we're going to think about saying that as the predicted price should go down by about $2.77 thousand when Mazda 6 increases from 0 to 1. So really more in context, this is telling us how much smaller we expect the mean Mazda 6 car to be compared to the Accord. And if you go over and look at the Mazda 6 versus the Honda Accord, you can see that it is, in fact, with rounding, about $2.77 thousand less. And we could interpret the maxima in a similar way. So this gives us a sense of how the prices compare. Okay, so in general, when we have a categorical variable that has k categories, we're going to introduce indicator variables, but remember, we're always going to do one less than the number of categories. And so a very simple model that just involves to predict a value y based on just the various values of the indicator function would look like this. Okay, and what we call the reference category is a category that's not included. So in our case, that was the Accord. Okay, so this is the model, really the population model, that we're trying to estimate right now. It's a very simple model. It's just trying to predict price based on the type of car. And there it is. Okay, this next graph shows a scatter plot. When we're going to now, we might be thinking, and it's fair to think that price of a car is related, in addition to the car type, its mileage. So there's a scatter plot that shows price versus mileage broken up, and the different colors represent the car types. Honda's blue, red's Maxima, and green is Mazda. Okay, so now here's our population model that we're going to try and fit. Again, keep in mind that we're adding a new variable to the model, that is mileage. Certainly there seems to be some association, Cars that have more mileage are cheaper than cars that do not. Okay, so what we want to think about now is to just look at fitting this model. And so this model that we just had, here's the fitted model, the population model I just showed you, that takes into account both the car's mileage and its type. And so you can see the scatter plot with the fitted lines here, and then also the Minitab output. Okay, I strongly suggest you look at page 177 for a review on how to interpret these slope coefficients in this model. Okay, so a couple of questions we want to ask. Question one is, what's the average difference between or is the average difference between prices for car types, statistically significant? So do we need to adjust, in other words, the intercepts? Do we really need to adjust the intercepts? Or can we just use the same regression line? Okay, in other words, does the type of car matter? And the second question we want to look at, it has to do with slopes. Can we have just a common slope for the regression line, or should we use different slopes depending on the type of car? So we'll look at both of those questions now. So looking at this Minitab output from the model that involves mileage in car, you should, if you run this, get this output. Okay, and so first off, if you just look at the p-values for each of these variables, they all look pretty significant. I mean, the Mazda is a little bit higher, but still not too bad. So we can conclude that, we want to leave all of those terms in our model, and it does seem to be important to have, in other words, different y-intercepts. So we can see that as the average price is decreasing as the mileage increases for all three types of cars. Okay, so the second question was, again, do we need to is it important or effective to use different slopes for the model? In other words, depending on the type of cars. And that means, in other words, in our language, should we add interaction terms? And so the model would look like this. We still have miles, we still have the type of car, Mazda or Maxima, but now we're going to put in some interaction terms, because if the slope is going to be different, depending on the type of car, we'll want to include these terms. Again, I strongly suggest in this case that you carefully read page 179 to see how to interpret these slope coefficients. Okay, and so here's the output that we get when we run, and we're going to assess this in a moment. That's the Minitab output. So the question is, are different slopes really needed? And if you take a look at the scatter plots with the best fit line using the model that we just suggested that had the interaction terms, what we can see is that if you look at these p-values for the interaction terms, neither one of the terms seems to be significant. But remember, we do need to be careful drawing conclusions just based on the p-value here because the interaction terms depend on mile and the type of car. So instead what we might want to do is to use a nested f-test to help determine. So are the different slopes really needed? There is this model that includes each of the separate terms together with the interaction terms. And if you run that model, fit that model with Minitab, you should get this. So the null hypothesis we'll want to run is, do we really need to have different slopes? In other words, is it possible to toss out this term and this term? And if you run the nested f-test using the Minitab output, and remember, you'll have to do a couple of hand calculations to do that test, you should get an f-test statistic of 0.26 and a high value, a p-value of 0.77. So what this is telling us, these extra terms, right, this term and this term, that we use, the interaction terms that we use to allow for different slopes, doesn't give us a better model. So we really don't need those, we don't really need to model for the different slopes. Okay, so just going back at just the more simple model now that looks at modeling price based on mileage, and then the types of cars, Mazda, and the other car, whatever it was, not the Accord. Okay, whatever it is. In this situation here, if we look at the 4-in-1 plots, constant variance seems okay, normality doesn't seem to be an issue. So this looks like we can use this model maybe to do some hypothesis testing or confidence intervals. Okay, so let's go ahead and that model that we have now. So our model is just going to predict price based on mileage and the type of car, and that's it. So this is a model that we're using. We've deemed this to be our best fit model, if you will. Okay, so I want to use it now to do a confidence interval and a prediction interval to interpret maybe what the average price is or predicted price of a car. And let's say for a car that has 75,000 miles. So we've done this before. Remember, you click on regression, and then predict. But folks, before you do this, make sure you run this model again. In Minitab, the last model you had involved interaction terms. And so begin by doing regression, fit regression model, and fit it just with these variables. Once you do that, then go back in and predict. A pop-up window will appear, and the pop-up window will give you this. So what you want to enter here is you want to response is price, and then you're going to try and predict cars that have 75,000 miles. And the Accord is this situation. The Accord is when the Mazda 6 is 0 and the Maxima is 0. And then you want to also predict it for the Mazda 6. So this is 1 and Mazda 0, and of course Accord is 0. And then in the last situation, this is when you're predicting for Maximas. In other words, Mazda 6 is 0, as is Accord. Okay. So if you enter that in, what you should get in part, you'll get more output than what I have here, but this is in part what you'll get. So notice that this is giving what this information is doing, since Mazda and Maxima are both 0, this is going to predict prices for the Accord. Accords that have 75,000 miles. And so you get this confidence interval, right? And you can say that roughly that we're 95% confident that the average price of a used Accord with about 75,000 miles is somewhere between about $10.6 thousand and $12.8 thousand. And you could say something similar for the prediction interval. In the Minitab output, you'll see you'll get similar output for both the other two types of cars. Okay, so that ends section 4.5.